All right. Good afternoon, family and friends. Today, I want us to look at about moment in physics, and thereafter we go to the applications of moment. Down there, we also look at the principle which guides us on the turning on the moment itself. So, without wasting much of the time, let me introduce you to this. We're going to be looking at the moment. Now, in most cases, this the moment has got a wide range of application in our lives. Okay, the way we apply this before I even introduce it to you, when you have a bottle, then you want to remove the bottle top. If you are to use your hands, the amount of force you can apply when you want to remove the bottle top is way bigger than the amount of force that you can use to open when you use an opener. That itself is a moment. The other one is that if you look at this, I haven't yet bought a door. I haven't yet bought a board. This is the door that I'm using. Now, there are reasons as to why the handle is placed there very far away from the hinges. It is because when you want to open the door, the amount of force you're going to apply in pushing the door from that far end is the same, is not the same amount of force that you can apply in opening the same door if the handle was so close to the hinges. Why? It is because it's because of the realization of this moment. There are many ways in which this moment is applied in our day-to-day life activities. So, what is moment? Moment is in simple terms, I'm going to say, is the turning effect of a force about a point. About a point. Yeah, that's a simple definition that I can give for moment. I'm saying moment, this is the turning effect of a force about at a certain point. Now, if you consider, that's a very simple definition that I've given, but if you consider an object such as a seesaw, which will be supported here, then you're going to have two people, one sitting here, the other one sitting there. But we understand that this person is here has got mass, and then mass times the gravity will give us the weight. So this, which is an example of a force. So this person who is here is exerting a certain amount of force in a downward direction, which I can call F1. Then this person who's also seated here has got a mass. Mass times gravity gives us the weight. So this person here and the weight is an example of a force. Is also exerting a force in a downward direction. But now, if we consider this point here where this beam is supported, this one is called pivot or fulcrum. Now, here where this rod is supported is called the pivot. But if you consider the distance from here up to where the point is at the of application, if you consider distance from the pivot up to the point where the force is applied, for this person here on the left who applied the force 1, we are going to call it distance 1. And if you consider the distance from where the pivot is up to where the person is who has applied force 2, this distance here, we are going to call it distance 2. But now, If you consider this, there are times where you're going to find if this person has got more mass, if the distance from here up to there, the distance here is D1 is equal to D2, if distance 1 is equal to D2, and then if the mass of this person, if the amount of force applied by person, this person here is way bigger than the amount of force that this person applies at this point, we are going to see the seesaw going in the downward direction in that arrangement. And if you look at the way the watch is, the watch is the watch go the wall clock that which gives the indication of how much time we have. It goes in this direction. So this direction is called a clockwise direction. But the way in the direction in which this seesaw will go when a person who applies force 1 is bigger than the force that force 2 applies, the seesaw will go in this direction. And this direction is called anti-clockwise direction. But if we get to have this person who sat here sits now on this end, and the person who sat here sits on this end, you will find that the seesaw will go now in an opposite direction, in that direction, and this end will go right up. And this is the indication of the clockwise direction, which I had explained earlier. So this one is called a clockwise direction. But if the amount of force 1 applied is equal to force 2, and if distance 1 is equal to distance 2, this object will not bend in any direction. If distance 1 is equal to distance 2, force 1 is equal to force 2, therefore then this seesaw will not move in any direction. It will be in equilibrium, or it will balance. So from there, that's where we can now define moment in a perfect way. So what is moment? Other than this simple definition, which is given that moment, the turning effect of a force about a point, I'm going to give you now a complete way. What causes, you're saying turning effect, what causes this seesaw to turn in a particular direction? It is because of the force that is applied and the consideration of the distance from the point where the force is applied up to the pivot. So from that, we can give now a full definition of the word moment. What is moment? Moment, in other terms, is said to be the product. Moment is the product of the force. That force is the one which is applied. So if you don't want to define it in this way, you can say that moment is a product. Moment is a product of the force that is applied, and the perpendicular distance, distance from the line of action. So why have we defined the moment in a different way from this? What you're trying to concede is this: if you have this object here, like the way I had indicated, and this is your pivot, if the force is applied here or hand, okay, if this force is applied in a downward direction, then the distance from here up to here is what we are calling the perpendicular distance. Now, why are we saying perpendicular distance? It is because this force perpendicular, the pivot is the object is in that direction. Then the force which is applied at 90 degrees. That's why we have used the term perpendicular. Perpendicular is trying to remind us that the application of force is at 90 degrees to the direction of the object. We're saying that the moment is the product of the force and the perpendicular distance from the line of action. What does that mean? We're saying when you're finding, I'm trying to drive the formula, we are saying when you're finding moment will only be found. And by the way, the word product used, we know certain terminologies when we're in grade 7. The grade 7 teacher would tell us about the product, what a product is, what a sum is, what the difference is. We know that the difference is the answer you find after subtracting. Then product is the answer you find after multiplication. So we are saying that for us to find the moment, we need to multiply so that the answer of our product, we need to multiply the force and the distance. We are saying that the product of the force and the perpendicular distance. So for us to find the moment, the formula is moment is equal to force times the distance. But we need to be reminded that the force must be in Newton, and then the distance must be in meters. If the distance is given centimeters, we have to convert to meters. Whenever you're carrying out a calculation in physics, you have to make sure that the data provided is in its SI units. So because of that, the units for moment, the units will be Newton meter. That will be the units for moment, because we are multiplying the force whose units are newtons and the distance whose units are masses, whose units is meters. Now let me take you through how we can do some calculations basing on moment. But maybe before I get to that, let me try to look at the application of moment. Where do we apply this moment? This principle is very vital in our day-to-day activity. Where do we apply this moment? Remember, like I said at first, say moment is very much useful in one, opening the bottle using an opener. Two, when you're trying to open the door. In opening the door, what you apply is moment. That is the reason as to why the handle of the door is placed far away from the hinges, because the shorter the distance from the pivot, remember the pivot of the door or the turning point of the door are the hinges. So the shorter the distance from the pivot up to where the handle will be placed, that distance will be very short. When you multiply the amount of force you apply and the distance, the moment you are going to find will not be equal to if you apply the same amount of force but very far away from the pivot. So we're saying the application one, bottle top opening. There are times you find this opener which is very short. If the opener is very short, it means the amount of force you're going to apply in opening the bottle top will be greater than if the opener was very far. The amount of force you can apply is very small. So one, the application is when you're opening the bottle top. Then two, we use this in the door opening. Door opening. There are quite a lot. Three in unscrewing the nut, you find that if a spanner is very short, the amount of force we're going to apply to unscrew or tighten the nut will be far much bigger than if the spanner was very fine. Find that if the spanner was very long, the amount of force you apply is relatively small. Okay, so let's see how we can make use of the moment formula. How can we use of the moment formula? How can we use the moment formula? Remember, we said that the moment is the product of the perpendicular distance from the line of action and the applied force. So let me say example. The example there. If you are given a meter rule like that, then this part here is fixed on the wall, which we can call pivot. The pivot there. Then if the pivot starts from here, then the force is applied at that point, where the distance, if this is 0 centimeter and this is 80 centimeter, so that is our 80 centimeter there, mark, and then the amount of force applied, then the amount of force applied here is 250. Okay, let me just put a very small number. If the amount of force applied there is 20, so if the amount of force applied here is 20 Newton, then the question goes like, calculate the moment produced, calculate the moment produced by the force. If the question goes like, calculate the moment produced by the force, what are we going to do? We go back to what I said earlier to say, whenever the question is given, you make sure that the data is provided in their SI units. The force, quite all right, is in newtons, 20 newtons. That's very good. The other thing that we need to consider is the distance. The distance is 80 centimeter. But remember, I said the units for distance are meters. So we're going to have that. We divide by 100 because there are 100 centimeters that make up a meter, and that will be 0.8 meters. And once that is attained, then you're going to say that a moment is equal to force times distance. The force which is applied here is 20 Newton times the distance is 0.8 meters. And once we multiply the two, 20 times 0.8, we're going to have 16 Newton meter. So this is a moment, this is a turning effect of the force about that point. It means if this object was to move in a clockwise direction, what is causing it to move? It is because of this moment, which is 16 Newton meter. Now, there is a principle. There is a principle that guides us on this. There is a very vital principle that guides us on this, on the moment. This one talks about two moments acting on one object, such as if we had a seesaw. If you can allow me to go back to what I was explaining. If we can have a seesaw with the pivot in the middle, and then having two objects at either ends of the base of an object, such as a meter rule. The object on the right applies the force in a clockwise direction. The object on the right applies the force in anti-clockwise direction. On which side will the object go? On which side will the object move? And what is it that is causing it to move? And if it does not move, what can we say about it? So that principle which guides us is called principles of moment. Principles of moment. Now, I will not state the principles of moment. First, I'm going to explain with a diagram. When you have a diagram, when you have an object here, okay, this is our rod. On the left, we have force 1. Here we have a pivot. Remember, this is a pivot. Then on the right, we have force 2. From this point up to the pivot, we have this distance, which is called the distance 1. Distance 1. Then from this end up to that end, we have what is called distance 2. Now, I remember saying that if the amount of force applied here, F1, is equal to F2, and if the distance from point of action F1 and the pivot is the same as the distance from the pivot up to the point of action, therefore this object will not move in any direction. Therefore, this object will be in equilibrium, or this object will balance. Now, for this object to be in equilibrium, it is because the sum of the anti-clockwise moment is the sum of the clockwise moment. So the principles of moment states that for an object to be in equilibrium or to balance, equilibrium, for it to be in equilibrium, the sum of the anti-clockwise moment, sum of anti-clockwise moment, clockwise moment must be equal to the sum of clockwise moment. Clockwise moment. So that's what the principles of moment states. It states that for an object to be in equilibrium, or for it to balance, it is because the sum of the anti-clockwise moment is the same as the sum of the clockwise moment. From here, what can we say? The anti-clockwise moment, the one which is on the left, so will be found by F1 times distance 1. F1 times distance 1 must be the same as F2 times distance 2. That is what you can retrieve from, or that's what you can derive from the states, from the principles of moment. Saying that the sum of the anti-clockwise moment, the way the sum, it is because at times we can have two forces acting on the same direction. We can have F1 here and F1 here, another F here. So we can have the moment produced by this force and the moment produced by the other force. So when you add them, it will give you the sum of the anti-clockwise moment. The times you can have one force applied here, another one applied here. So these two forces that are acting at different from different points, you can have the moment produced by this force, the moment produced by the other force, you add them, which will give you the sum of the clockwise moment. Now let's look at how we can make use of this formula in a practical way. I'm going to get some few examples from my pamphlet. So at times they ask, state the conditions that must be applied for an object to be in equilibrium. For an object to balance, what are the conditions? The only condition that I can advise you to speak of is the sum of the clockwise moment must be equal to the sum of the anti-clockwise moment. Sum for an object to balance, sum of the clockwise moment must be equal to the sum of the anti-clockwise moment. Let me give an example. Let me give an example. Here we are. So example, the application of moment. Example, we have this object. Okay, the pivot is somewhere here. The distance d2 is in meter. Then down here, 100 newtons of force applied. Then force 1 is not given. Then the distance from the line of action up to the pivot, the distance there is the distance there is 0.5 meter. Then the question goes like, calculate the force F if it is balanced. The question goes like, calculate the force F, this F here, to get the force F1 if the object balances. So what are we going to do? If this object is balanced, we go to the principles of moment, which states that the sum of the anti-clockwise moment is same as the force the sum of the clockwise moment. So what we are going to do is say F1 times the distance 1 will be equal to F2 times the distance 2. So what is our F1? Our F1 is what we are told to find. We're going to say F1 times distance 1 is 0.5 meters, which will be equal to F2 is 100 newtons times the distance 2 is 0.4 meters. But we are looking for F1. So we are going to divide by 0.5. We also divide here by 0.5. Okay, so that 0.5 and 0.5 will cancel, and then our F1 will be equal to, so when you get your calculator, the 100 times 0.4, then later on you come and divide with the you come and divide with the with the 0.5, the answer will be 80 newtons. The answer will be 8. So that means at this point, our F1 will be 80 newtons. But now, what can we? This is meters. This is meters. At meters and meter cancel. The only units that will remain will be newtons. But what can we see from here is the longer the distance, the shorter the amount of force that you can apply. And the shorter the distance, this is 0.5. The shorter the 0.4 distance, the larger that is applied for the moment to be equal. Why it is because a distance from the point of action up to the pivot has a role to play. That is the reason as to why the handle doors or the handle doors are placed far away from the hinge, which is the pivot, so that